Thanks and to Sana and to all of you for being here. I have made some notes, and as I am talking, please feel free to interrupt me, and we will take turns talking, and if I miss something, Dayadeep will add or point out. So we will start. I'm getting recorded, but I'm still going to say this. In institute, if you look at the course structure, most of the core courses are listed as 2106 or 2026. What it means is that every week you are supposed to teach 2 lectures and have 1 tutorial. If it is 2106. If it is 2026, it means that you will teach 2 hours of lecture and they have to do 2 hours of lab on their own, and that is what counts as 6 credits. Recently, even previously when 210 was there, many core courses were running without any tutorial component, which goes against what Sridhar was telling about sufficiently and timely people doing themselves. So it makes a huge difference if you have these tutorial sessions or not as far as student learning is concerned. And what is worse, with the new less number of courses that departments are being forced to take, I have heard of this strategy that many courses are being made into 2026 with the understanding that 4 hours of lecturing will be available, okay? Which is a completely wrong way to go about doing things. Like I said, maybe we will cut this out of the lecture, but but what I want to emphasize is that there is a good reason why it is 2106 or 2026, and even if your course is not, it is worthwhile running it like that, because we have done several such courses and we have found that it is very, very effective. Specifically, we are going to talk about courses where this hands-on component also has a computational aspect built into it, which is very important because many things, for example, traditionally thermodynamics would have been taught in a metallurgy material science department, is different from actual practice in the industry today, because lots of computer-based programs are available and lots of computations are done using these programs. And students who know all the concepts of thermodynamics and can solve all the problems that are there in the classic textbooks will still find it very difficult in practice if they have to use any of this, because that is not how the industry works anymore. They are no longer looking at charts, they are no longer making these calculations, they are no longer using these rules of thumb. Everything is getting replaced by a program on which you have to input, you have to get the output. More importantly, if the output doesn't make sense, or if it gives something, you need to know whether one more calculation or one more test is needed, or you can accept the result as is. This is not possible unless students are trained to do this as part of the course itself. So this is just one example. Many courses that I have taught in our department: modeling analysis, simulation optimization, diffusion and kinetics, and modeling microstructure evolution, data analysis and interpretation, and we are going to teach AI and data science. In all of this, there is always a computational component, and that could be R, that could be Octave, that could be C, very rarely, but sometimes, that could be Python. Dayadeep has taught numerical methods analysis.
It's essentially it's a programming course, but we focus on using numerical methods.
So there is always use for this, and in this respect I just wanted to give some tips that had worked for us and tell you why it works, and some things that we have tried and does not work and why I think they don't work, but this is open for discussion. I'm not telling any final word here, but just for you to think about, and you can also share your experience and or what you think could be done. We always found that it is useful to have open source software available for students. It saves lots of trouble for you as instructor as well as for the students, because open source preferably things that they can also download and load on a Windows machine, because most of us use Linux. but many students have Windows machines. So something that can be loaded on Mac, Windows, Linux, and open source works very well. Octave works very well. Okay. I have had the faculty colleagues come and tell me that why are you using Octave? Students are only trying to do Octave. They should do it in C. It's not efficient and so on. But Octave can be loaded with fairly easily with some help from the TAs. So open source helps because then everybody has access to it. Most of the students have laptop. During pandemic, they use their own laptops to load R, for example. And then we had tutorial sessions on that, and the final exam for the R part was a Viva, where they have to share the screen with me and do a modification or show the code, and I asked them to modify something or run something, plot something. They will do it, and that's how they got evaluated. During this process, we found that everybody has a laptop. The only problem is sometimes the specifications are such that you cannot really make them run large codes. In Octave, plotting a 3D plot might be too much, but up to 2D, up to plots or multiple plots and so on. So you just need to know what is possible with the specifications they have. But open source is very, very helpful. One thing that we tried, and at least it didn't work for my classes, is that initially I had this idea that I have this data analysis course. In Moodle, I have loaded the data. So everybody downloads, and visualization, suppose we want to do, we had 100 years of monsoon rain data, for example, for different parts of India. Okay, so you can take this data, you can visualize in many different ways, look at different aspects and so on. So as I do, can the students do in the class? And this fails, and it failed miserably for me. And the reason is that different students take different amounts of time to do the same task. They all are capable of doing it. They can and on their own accomplish it, except that for some people it takes a few minutes, and for some people it takes slightly longer. Some people it takes measurably longer. I mean, it could be that I am showing a script, it could be 3-line script, and you will see some 20-30% of the class immediately got it on their screens. They get the same thing, and another 20-30% of class takes some time, couple of minutes, and they have got it. And then there is one more part of the class. At this point you are in a difficult position because you cannot move on, because you still have 30-40% of the class which hasn't completed the task and they feel left out. And if you spend more time on them, this works if the class is small and you have large number of TAs. We have done workshops like this. Up to 3 participants, 1 TA. If you have some 30 participants and you have 10 TAs roaming around, this works well. But in a large class, this doesn't. Okay, anything beyond 60 students and we don't have so many TAs. So, because of which, what we always did afterwards is to write detailed tutorials. The tutorial is like, okay, open the R window, type help, enter, then you should see this, and then write help sign, you should see this. So there was this screenshot for every step, and the tutorials were also done in such a way that an average student would complete this task within the class hour. And if the student is slightly quicker, then there were more exercise problems, so they can move on to the exercise problems. But 90% of what your learning outcome is, that should be met even for the students who completes only 50% of the tutorial. Okay, so keeping this in mind, right? I mean, the tutorial might be for plotting. Maybe some student is trying to do 3-dimensional plots, but at least given some x, y, are they able to get a plot, label the axis and so on? That should be done by almost 90-95% of the class within the hour. But writing these detailed tutorials also are useful, especially if they are using open source, in the sense that they have access to it. So afterwards they can continue doing it, and next class they can come. So everybody is again on the same page with respect to doing the next tutorial. So writing out detailed tutorials help us. And making them install the software is one exercise for which they always get 5 points in our courses, whether it is R or Octave or Python and so on, which is also a very useful skill for them to have. And sometimes there have been disasters. Some students got over enthusiastic. They wanted to have Linux also installed, lost everything on their laptop, but they have been more forgiving about us. But it always works, and the first time they achieve the same thing that the instructor is showing in terms of the output of a code or a plot. It's a very nice experience for everybody, for the instructor as well as for the students. So I mean, open source, so you can make them install, that is always useful. And another thing that we tried and were not very successful is giving projects. See, sometimes it looks like, okay, I want to teach R, let them take up a project and do. There are two reasons why projects are difficult. One is that students have a tendency to postpone everything. And if it is a large class, it is not possible to continuously assess all students and give feedback as to what they are doing and how they are doing. And so the learning becomes lesser and lesser, and there is no uniformity with respect to the minimum that everybody learns. I mean, some students might really do more than what is needed, and some students might just scrape by doing the minimal thing. But having these kind of piecemeal tutorials every week is helpful. What works is, after they all get to some level of expertise, then you give a slightly bigger project, and that can even be with smaller groups. Then they have all the required skills, and putting it together and solving a bigger problem then is also within their reach, and they will also be engaged enough to do it. So, but especially large classes, projects never work for me. But I mean, again, it's my experience. I think Dayadeep ran the course in project mode, right?
Yeah, but that was a smaller. It was a smaller class.
So you want to share that project thing?
Yeah. So what helps there is a well-defined structure. So if you tell them that, okay, there are going to be 4 stages in the project. You know, in the first stage, all you do is present the algorithm. Write down the algorithm, present it. In the next stage, you know, have pseudocode ready. In the third stage, have a first draft of the code ready and show that it solves one problem. In the final stage, you know, show that this code can be used to solve a more general problem. And maybe you can even extend it to say, okay, now each group will be assigned someone else's code, and you have to solve a problem using that. So I think the key here, and I'm looking forward to what Avinash has to say, because he'll be talking about projects. The key to doing projects well, in my experience and from what others have shared, is you have to really plan out what you expect them to be able to do. And then have checks in place at each stage. So you have to get the manpower ready. So if you need TAs, you need to know before the course starts how many people you need. You need to train them, tell them what the expectations are, and so on. So if you want to do projects, there's a lot more preparation that is required. It's difficult to just, you know, leave it up to the students, and, you know, then the outliers will do well, but the rest of the class will probably not do very well. So projects are difficult. That's the underlying message. It can be done, but a lot of preparation.
Do that well, because I had that issue in my course, that I tried to tell them that we are opening up the black box and I want you to be able to code it and understand what is happening behind. But I had difficulty, or at least the students didn't seem to get that message at the end of the course.
Yeah, most of the problems that they do in the the question is, students, it is easier to make them use a black box software, click something or GUI, and get a solution. But if you want to build from brass tacks or from the basic thing or implement it yourself and so on, they are not keen, right? Or they are not that much engaged. That is the question. How do we deal with this? There are two things. One is that some of the things, like for example, for the optimization course, when I use Octave, the textbook that I choose is one where there are algorithms given for each one of these. If it is BFGS or Newton-Markart, there are algorithms. Of course, one of them is implemented in Octave as a function call. The exercise for the students is to take one example problem, solve it using the function call, and show how well it performs with respect to what they themselves have written. And that is part of the tutorial. Everybody gets that this thing, and they have to implement. And some of them are also more open-ended. In the computational lab, Preeta is not here. What we did is we took a stress strain data from the lab. In the lab, there is a computer, there is an associated program that comes with the machine which plots the stress strain curve and gives what the Young's modulus is. But we also got the raw data, and these students have done that experiment in their lab, so they know how the lab plot looks on the machine. And we gave them the raw data and asked them to now do a similar thing using any algorithm they think is okay, because the data is noisy. Without any stress, there is a strain, or there is some stress but the strain is negative, which does not make sense. So there is lots of data cleaning that they have to learn, and they learn it by looking at it themselves. Okay, this is the kind of data that comes out, and whatever you see as nice plot is not before you do lots of massaging of the data. So one of them is to make them do this. I also have a colleague who teaches molecular dynamics. Mostly they use LAMPS, GROMACS, etc. in the class. There what he does is to give them scripts, ask them to make modifications or find errors, correct and so on. But the first exercise is always, take some 10 particles in a box, maybe it is just 2D, just for them to know the different steps. Take some Frankel-Schmidt, do the first 5 algorithms, then we go to discuss the black box software that we are going to use. Okay, so that is one way to make them get engaged, see that things might look very smooth, but there is a lot more effort involved. Neighbor list, for example, unless they do it, they will not realize how much effort is involved in. So that is one way that can be, and probably in your numerical methods also, instead of function calls, they wrote some scripts.
Yeah. So but I guess one of the intents from you in asking that question was, how do we motivate them to look at the actual machinery? Right. So, and as Guru said, that you have to give them motivating examples. So you have to create examples where you know that the black box is going to stumble, or the black box may give them answers which are absurd. So that then leads them to, or hopefully leads them to ask more questions about what is the black box doing. There's an algorithm, but the algorithm is not just a simple sequence of steps. There's a lot of checking that needs to happen, and what we keep stressing in classrooms, that okay, as an engineer you should have a sense for the numbers which are coming out. If you're expecting kilopascals, you should not be getting terapascals in your output. For zero strain, there shouldn't be a stress, or there shouldn't be a negative stress shown. So giving them examples where a black box will struggle, or giving them data which is or you intentionally make it dirty, or you collect it and that okay, it's not great, it's not clean. So sort of showing them what is required, what is needed, and then that hopefully gets them to question what is happening in the black box. and then try to recreate what's happening in the black box to make a better implementation of whatever they're trying to do.
Yeah, so to take this answer to a slightly more abstract level, see, I think it's our responsibility to tell students why they should care. So if you want them to look into the black box, I mean, just because you were excited to look into the black box does not mean that your student is going to be excited to look into the black box. So we have to give that argument as to why we are making them do something. I think that is the key. So I often have a slide which just says this: why should you care? And sometimes that argument does not work for me also. I say, look, if it's not convincing me, how is it going to convince them? Right? Like, for example, if you take programming, right? When I learned programming, we were doing assembly programming. Okay, and when at some point you feel everybody should know assembly programming. Okay, who knows assembly programming? Right? Nobody cares. So things move along, and that why should you care to learn about this? Like, either in the form of saying that, look, real data is like this, it's messy. You need to know what's inside the black box. Some argument like that has to be given.
I think maybe I have a solution to this thing. My PhD supervisor actually used this technique and I applied that. So, I mean, for example, there is a tool PIV lab which we use to track particles in a flow. Now there is an inbuilt software which one can simply use, and it's a plug and play sort of thing. So whenever I used to do this thing, my supervisor used to ask me that how did you get this parameter? Just explain that. And what changes can I make that this parameter becomes of this value and so on. So this sort of question then forces a student to sort of go into detail what exactly is going on. And then one starts to work from scratch and explore the black box. So I think I found that to be interesting.
I don't know if this is a forum to discuss this, but we do have branches of engineering where students are increasingly losing interest in the core subjects because they have a specific target in mind. So that becomes a challenge. I was wondering if you have any suggestions on that.
So again, I'm on record, but I'm going to go ahead and say it. Metallurgical engineering and material science is one of those branches where students are not too keen. But I think that is because they don't understand, because they don't realize that I'm reading a book called Being You, which is about some neuroscience, but they are talking about some free energy principle, which is supposed to explain how the brain works and so on, or how brain is a Bayesian machine, right? Similarly, there are lots of things and concepts and analytical skills that students can learn. Like I mentioned, all these courses, a computational lab is there, data analysis and interpretation is there, modeling and analysis is there, simulation and optimization is there, microstructure evolution modeling is there. All these courses are from our department, and some of them are core courses, which means if the students understand that the skills that they are learning, maybe they are using it for a reactor now, but the same set of skills will be useful for them even if they leave the so-called core and do something else. That if we can convince them, we have a more receptive audience. That sometimes does not happen, like Sridhar said, it's because of our own training, right? If I go into a class and because of my training I want to talk about iron making, steel making, and that looks like a done to death subject or some industry in which they are not really keen on going and working. But maybe if it is a fab or a semiconductor or silicon making, it interests them. But we are still picking examples from iron making, steel making because our classical textbooks are all written using iron making, steel making, right? I don't have to put more effort, look up data. You will find this if you want to do a data course. It is very difficult to come by reliable data which students can use at scale and learn things. So it takes lots of effort, but I think it is worth. I mean, one of the ways, like saying, why do we care? One is to tell them. Second is to make them realize it themselves. I don't tell, but I tell that, okay, you have done it in the lab, same data, look, I have taken the raw data, now you do it and show me how it happens. Because nowadays softwares are so advanced and they do so many things which they don't let the user know, right? So it's very easy to trick them, saying that, and then in the class I say, no, what are you saying? You got this and this piece, you can go collect the data yourself, bring it, and then it shows a nice figure you are not showing. So it's basically somehow tricking them to realize that it is worth learning, because finally the branches are there for our convenience. I don't think, and I don't think students realize this. Again, on record, I don't think even some of our colleagues realize this. Okay. Finally, problems come. Yeah.
You mentioned, you said this yourself. It takes finding the correct examples to give in class takes a lot of time.
A lot of effort. Yeah.
And most of us, all of us, have far too many demands on our time as it is. How much time is one expected to set aside for a six credit course per semester?
At the beginning, when one starts teaching, it would be about 40% of the time.
Yeah, I was hoping you wouldn't say.
1 hour class, preparing for a 1 hour class. So if it takes you 6-7 hours to prepare for a 1 hour class, you're doing okay. Okay. Even now, like even this talk which I just gave, which I have given I don't know how many times. Okay. I took 4 hours yesterday, making one new example, thinking about, will this work or not. So yeah, so even when you get experience, it's 1:2.
That is why when you are teaching first time, don't give more than 2 lectures per week. The third hour should be the students engaging and doing something in a tutorial, right? You always have a set of tutorials ready, and there were times when I couldn't prepare for the lecture. I went and said, okay, today is tutorial.
You brought up an excellent point. Is something I wanted to address anyway. The first time, or even the second time that you're teaching, or even the nth time that you're teaching, it takes a lot of preparation. It takes a lot of time if you're invested in it. So don't feel like, okay, I am the only one who's spending for a 3 hour per week. I'm spending 12 or 20 or whatever the number is for you. It happens to anyone who is invested. You have to put in that much of time. So you budget time accordingly. And as Guru said, it's excellent investment if you can create a set of simple tutorials. They don't need complex things. That's one of the mistakes we make as teachers, that we think that we are always trying to address the top 1/3 of the class. But I think that's a mistake. The top 1/3 is going to do well anyway. It's the next 1/3 and the bottom 1/3 that we should really be invested in. That's my opinion.
I agree with all of it, but one thing that's worked is to these examples, to also seek from others. In the sense, there are other senior colleagues who may have taught it. Many people would have taught it differently, but if we find someone who's thinking like us, who may be doing more examples and all, they may have taught it 10 years ago. In department offices, so in 2010, I taught a course in the physics department. For the first year course, there were these binders, this thick, and 10 of them. Electricity and magnetism has been taught for the last 40 years, and they were like 40 years worth of things. So just going and flipping through it, that took some time, but I didn't have to create every new problem, every new example. A lot of it had been done. Some of them had retired. But it's finding those 2 or 3 people who you would think like you, and getting, maybe it's from some other department also, these common courses. So that has worked to some extent.
So at the coming semester, I'm teaching a course on econometrics, which is 6 credits, and there is another tutorial essentially for 3 credits. So for the econometrics course, I think I'll be teaching it for the 3rd time. But last 2 times, the syllabus that I've prepared, so if it's 1 hour lectures thrice a week, then almost till right up to the before the exams, I've had lectures and done some examples and interactions. So now if I want to engage the students more. So I'm like already, in terms of the course curriculum that I intend to finish, I will not have a lot of time unless I revisit or rethink as to how much content I deliver in class versus how much I expect them to do the background work and do some activities in class. So any advice on that?
So I will say, and then probably Dayadeep can. One thing that I found, the first mistake I made when I started teaching, and it took long time to correct, and even now I'm not sure if I have corrected, but I remember that during pandemic, for example, we talked to Sana because students felt that they were getting overwhelmed with the amount of material that we were giving out. But even before this, even when I was teaching in class, I now realize that there were two mistakes that I made. One is to think that the syllabus or curriculum that you get is sacrosanct and you have to complete the syllabus. Okay, which I think is the wrong way to go about. Probably, but unfortunately our curriculum is not written with learning outcomes, what they're supposed to know from this course to do something else and so on. There is a little bit of what is the prerequisite for this course and for what other courses this is a prerequisite. That much only you get. Unless you talk to some senior faculty members who have taught or part of the curriculum, you don't get that. The second thing is, I don't know about econometrics, but at least in many of our fields, I know that whatever I am teaching, by the time this student goes and joins the industry, at least 50% of it will be obsolete. There is going to be a different way of solving this, or maybe that material itself would have been replaced by something else. So what is more important that they should learn is how to learn something, not really, this should be just like a practice case, like the examples we give in the exams. So keeping these two in mind to answer the question, I think it is still worthwhile to sit down and decide what are the skills that I am expecting the students to have at the end of this, towards which this is working as this thing. And this comes back to evaluation also. For example, coding, we are saying programs and so on, there are umpteen number of codes that are available. So if you give an assignment or tutorial where students have access, I have seen students do it. They will open their mobile, they will search for some code and then they will enter and so on. So the only way to break that is by putting lots of effort in designing your questions, knowing that they are going to look up. So you allow them to look up, but you set it up in such a way that the learning still happens. That is, given a problem, how to mathematize it and solve it using this program is what I am looking for. And that is the context in which I was using that example of uniform probability and changing it completely. So they can go search forever online about cows in Jalvihar. They are not going to get, we know for sure. But there is a problem. I mean, it is for them to realize, okay, this is the same problem and he is putting something else, right? So my answer would be to sit down and do this exercise because it is worth doing and it also makes much better delivery for students. I mean, for longer they will remember the learning from this course and they will also use it later. Rather, if you are, I have these 14 weeks, 42 lectures, I'm going to use all of it, but how much did they get then becomes an issue. Yeah. So.
Yeah, essentially what he said. And some of it comes down to when he mentioned these things, that it's covering the course, what's in the course, versus what do you want them to be able to do? What do you want them to be able to demonstrate once they have done your course?
Parts of the syllabus is, it is uncomfortable, but so I speak from two separate experiences where very thoughtfully, let's say there is some principle and 3 different examples or 3 different, some sub-examples kind of a thing. So my postdoc advisor in the education department, he had taught me that do the first one in using active learning, get students to do it, maybe spend 2.5 times the time you would have normally spent lecturing. And give the second one for homework and the third one self-study. So I would actually not quote unquote teach the second and third example, or I don't mean just example, but let's say 3 topics which are similar to each other. I would only do the first one, but in more time. And we did some comparison in the exams and all. It was the same as the teacher teaching. The second one was where some of our students were doing some study that was, I think, Sridhar, in your class, the networking class. Again, where you had done one thing and made them learn it made them do it themselves, not taught that one, but they did okay on the exam. So we've seen cases where that works, but it takes a lot of time to decide which ones to remove from the coverage, so to say, and which ones to actually spend time on. But it's not that radical, and people have tried it. That's the point I wanted to make.
With all the new large language models that are available to assist students, have you seen some effect of those in courses that you offer? Do you have any comments on that?
Not that I know of. Maybe they have used, but I'm not sure. Because most of these are programming ones, but my students tell me that things like Python, it can still write small programs.
Right. So one of my colleagues told me last semester that one of the assignments that they had given, ChatGPT was able to get the answer in 10 minutes. It was not the direct answer, but 3 prompts gave them the solution. So there was some sort of a crisis that came up there.
Right.
And the same thing didn't happen in my course, but then I got a forward which basically showed me that, okay, ChatGPT could give that, subroutine in a minute, as opposed to them trying to bang their heads and, write that algorithm by themselves.
Yeah. So like I said, I don't know, but they might have done. But what I feel is that it is very hard. That is one of the reasons. When I give this programming assignments, people tell me that there are plagiarism checkers and you can put through every student's assignment and find out if they have plagiarized or not and so on. But I always find this other way, that I come up with a problem for which there is no straight answer. But conceptually, if they understand some other problem for which it is there, they will be able to solve this. To be a better way, because now we are allowing them to use the resources. They can look up. Similarly, like I said, my colleague, for example, LAMPS, there are lots of scripts. So you can't really come up with a new problem, especially if you are teaching a course. For research level problems, yes, they may have to do something. So his way of doing is that all the students will get a wrong script, for example. You now need to figure out why it is giving some nonsensical result. Or it is not executing, the script says some error. See, most of the times, especially in programming, students think that they can cut paste everything in Google and they will be able to solve the problem. They are not wrong. Most of the times they can do if they have enough time. But I keep telling them that I know programming means that I can give some commands, and if the computer says something I understand, they don't even read the error message. It clearly says line 28 and column 13 there is a syntax error. The student is still cutting pasting it on Google, right? So this kind of engagement you can bring in, or break this habit of just cut paste, take the first answer that is there in Stack Overflow or wherever and put it, by giving problems where they have to necessarily think. Right? The other one I said is to make yourself and compare with what is already there and show how it performs. Where they have to, again, you can give a project, say that, okay, get a ChatGPT code, write one which is better than that. Right? So we are allowing them to do, but we are still making them engage with what they are getting out of it. So I think that is a better way rather than policing. Sometimes the tendency is to say, okay, we will police. But I found that that is more draining, and probably Sundar is going to talk about Moodle. So there are ways of setting up questions, question banks, coming up with many different variations and so on. The effort that you put there is much more worthwhile than policing.
So out here, when you're talking about it, these are courses which are mostly theory, and there's some amount of practical, right?
No. So for example, simulation and optimization. was complete theory course. It just had 210.
Right. But now there are also these lab courses, and I'm thinking more about the lab course.
Right.
So how do you because lab courses are ideally supposed to be more hands-on anyway.
Right.
So how do you conduct those in a different way or in a way that's more effective?
One is, as much as possible, we reduce the group size. When we run the computational lab, it will be every student on a computer. Even though we could have finished the lab in one slot if we paired 2 students per computer. We had about 120 students at that time, we had 60 computers. But we still ran 2 sessions because as much as possible, the group size should be small. The ideal group size is 1 student. Okay, which means extra work. I mean, which means 2 days a week we have to spend in the lab rather than 1. And whoever I have taught with, that is another point that I have noted down. Many of these courses have more than 1 instructor, especially lab courses. And sometimes people take turns in going. So the students tend to see different instructors on different days or for different sessions, which is not a good idea. The student should see a single entity as the instructor. That might be 2 people, that might be the 2 instructors and TAs put together, maybe a staff member, but they should see this as one single entity, which means all of us are available all the time when the lab happens. Okay. Now, for labs, sometimes the resources are such that you cannot run. Then what is the smallest group with which you can run? And then how do you evaluate them? Because then also you will see some group coming and saying, oh, they got this guy who did all the work, or within a group somebody will come and say that, so there this kind of peer instruction works, because sometimes when you evaluate, you can say this is a group, you will be evaluated as a group, which means it is in the interest of one person to teach. And similarly, some of the group labs, first at the beginning itself, they have to tell you who is taking up what responsibility.
But is the assessment different when you're talking about a theory course or a lab course? Or you're talking about the same way that you have the same learning objectives? And
so, for example, for computational lab, we still use Moodle to evaluate.
Okay.
And we came up with the same question but in different forms or changing numbers and so on. So you can evaluate. But suppose, I mean, I've also taught other labs like solidification kind of labs, where, groups of 3 to 5 is common. There you have to also have an evaluation, which should be fair to the entire group. And you also want to make sure that everybody pitched in, which means at the beginning of the lab today, so okay, you are going to cast aluminum, tell me who is doing what. After the lab is over, I will ask questions, but that questions will be directed to individuals and that might not be related to what that person took up as responsibility. Like this person might say that, okay, my job is to melt this. But the question that I have might come to pouring or the casting structure. That is because it is the responsibility of the person who did the other thing to teach this person about that and for this person to teach the other person about. So when you set up the evaluation scheme, you can make it clear that you are going to evaluate them as a group at the end. But at the beginning, they still have to come and tell you what responsibility each person is taking. Which works well, that is, if they know that you are paying attention to these things, most of the times they will do a fair job.